Alright, time for another DraftPhysics.com. DebatePhysics.com also, but nobody to debate. Unfortunately, I can only do it in this fashion where, argument, counter argument, but no continuity. No counter argument. Yeah, so AlphaPhoenix, interesting channel. It's kind of like a 10-year-old Piro, except smarter. But anyway, oh god. Anyway, so I'd like to be able to persuade him to do a kinetic energy video. So I'm going to leave a comment asking. Maybe you could do that too. Because yeah, in 350 years there should be one video proving the existence of a theory, right? If they're going to say something's the truth, they ought to have at least one video demonstrating it to be somewhere close to the truth. But anyway, so he did do a video on wires and stuff, and there's always something you can find in all these videos where they say something where they're just saying it. This is the assumption you must accept. This is our, it's sort of their religious story, and it's, yeah, you have to believe, well, Jesus existed, okay, did Joseph really exist? Are these real characters, all these other people? Do I have to believe in all of them? So, we might be able to agree there's stuff called force and there's stuff called matter, but yeah, I don't think I'm going to agree with any kind of notion that there's some other thing called a field. It's a field of force. Um, you know, so in my book, that's the axiom, the starting point. So anyway, it all gets. They always got to cram. Anytime you talk about electricity, they always have to turn it into this wavy crap. And so I'm just going to argue through some of the wavy crap and just demonstrate that you don't have to think of it as magical waves. That the waves are made out of real things and it's real substances, and they're not really waving. Sort of like the ocean isn't really waving. The water's going up and down, and it's real water going up into gravity and then getting pushed down by gravity. Real water molecules are doing that. But anyway, yeah. So we don't need to play the video really. So I guess I will just draw what's in the video. So the subject is, the speed of electricity, and do you change it by changing the wire composition? And effectively, no. But it's a trick question in some respects because we can't turn on and off electricity perfectly, all or nothing. And that's part of the problem is, yes, some of the electricity will get someplace at the speed of light, but maybe all of it won't. So they're all kind of, it's a little more to the story than the story they tell. Anyway, yeah, that's probably enough. And then I can just draw shit. Alright, so there is a simulation he does, okay, where he shows electricity moving through the wire, and we can agree on something. That's the electrons are in the wire, and it's the electrons are basically just communicating the force, okay? The electrons are doing a tiny bit of movement. So they already know this about atoms, right? I mean, an atom is a grain of sand out in a football stadium, in the bleacher seats. And the nucleus is, on the 50-yard line. That's a huge amount of distance for these tiny little objects separated. And so the real separation between an electron is, it's gigantic. It's like if you were human-sized objects, you're talking about one person being in California and the other person being in New York. And the fact is that the force, okay, is going to communicate between these two pieces of matter. And so most of the movement, okay, I'm going to push you. You're in New York, I'm in California, let's say. I'm going to push you. So I'm going to send a force moving the speed of light. The force is going to hit you and move you 2 feet. Okay, so the 2 feet is a tiny amount of distance for the trip, right? So you can sort of understand that the fact that you're going a little tiny bit slower here, okay, you could be going a lot slower actually. Well, you can't go a lot slower. I mean, you can't go, you can't use up a whole bunch of time, but you can go pretty slow, relatively speaking. and it's not going to change the, all I do is change how fast the bullet's going. So if I change it from C to the speeding bullet, you can understand that you moving 10 feet a second wouldn't be much of a decline in speed. But anyway, all right, so I'm going to I'm going to be moved, and the fact is that what's really going to happen is I'm not going to do anything. Okay, I'm going to be moved. Okay, I'm an electron. I move into this space. This space is already being hit by forces like light. Okay, so you can sort of understand that that's sort of what I'm arguing here, is that I'm going to get hit by pieces of light. The light's going to reflect off of me in California. It's going to travel to you. And it's in fact going to be more light. So if you were really light sensitive and you could count exactly how many photons were hitting you from both sides and you moved based on that number, you could understand that, well, I just sent an extra piece that wasn't going to hit you. Because I'm here, I now reflected a piece of light, that light's going to hit you, and now you're going to get moved in this direction. So by existing and then by moving my position, I'm going to be sending more energy towards you, and it's going to move at the speed of light. So obviously most of the voyage is at the speed of light, and a tiny percentage is the electron. So the idea is in the wire, you could just extend this picture, and I suppose, blah, blah, blah. The separation between the electrons, okay, changes as you go through the wire, but the fact is the message being sent is being sent at the same speed for all of those changes, so it really doesn't make any difference. So even though there's more electrons here than there are here in terms of the space between them, the fact is they're going to send the signal, pretty fast to all of them, and they're all going to separate from each other. These are going to separate, they're going to try to, and these are trying to separate, and these are trying, So the electrons are always trying to get further away from each other, and it's only when some of their force keeps them together, like there's protons and nucleuses. So they're going to be wanting to stay attached to those. But the electrons are moving inside the atom. So you have an atom, and all that's really happening is the electrons are jiggling inside that space. And the fact is there are jiggling in the sense that if when I hit an electron, what happens to it? Well, it moves in a direction. All right, but as soon as it does that, it changes the balance of power and all these arrangements it has with these other electrons and the other forces. And it's also moving into a field that's going to, just like gravity, all right, there's a field, and when it moves into a direction, right, it's got stuff coming at it from both directions. If it moves into the field, it's going to be dragged, okay, there's going to be drag in the sense it's going to hit more stuff. And it's going to slow down and then stop, okay? And now it's going to be in a position where it can go the opposite way, because all these characters that put it here in the first place, it's still going to be in that circumstance where it's still attracted to the proton. So you're overcoming its attraction by throwing it into where it's not gravity, it's just drag. The drag is going to act just like gravity and stop it at a new position. But that new position is I'm attracted to the proton, so it's going to move back. And so the speed you pushed it, it's going to return to that velocity again, just like something returns to the Earth. It's going, so I lift it off at 10 miles an hour. It lands at 10 miles an hour. But the fact is, if the Earth wasn't there, okay, it would keep going, okay, until some other force stopped it. So unless you had, so if you could make the Earth transparent or something, you could oscillate, you could throw something 10 miles an hour and it would go up the other side 10 miles an hour and then go back up 10 miles an hour and it oscillates. So that's what electrons end up doing. They do some oscillating. And just like a pendulum, okay, that it doesn't really matter, when I'm swinging the pendulum, as it runs out of force, it's still, the period is the same. The amount of time is the same. So each swing comes at the same rate. I'm not changing the rate. I'm changing the amplitude. I'm changing how far it swings, not how fast it swings. So you can understand that if you were creating a condensation, a compression in the field, so you have a bunch of stuff in the field, a bunch of photon-like stuff that makes photons, little bits of force. And the fact is that you move into that field and reflect it. What you're really just doing is taking these 6 things and putting the 6 things in a smaller space. And so, well, 9 things now. So they're just filling, you take stuff that was in this much space and you put it in this much space by moving into it. So theoretically, my hand is pushing photons into a smaller amount of space. I'm increasing the number of the photons in a certain amount of space by pushing my hand. I'm compressing. Now, obviously, at these speeds, I'm not doing much to change the world, but the fact is it is a frequency. I'm compressing the force, putting more force in a smaller amount of space. So this is what space ends up being full of, is places where the stuff is further apart, and then places where it's closer together, and then places where it's further apart, and then places where it's closer together. And that's the frequencies, all right, in the universe. Now, you wouldn't call those waves. I mean, they're stuff moving in a direction, okay? They're all moving in the same direction. It's a bunch of birds flying in the same direction, or fish, or however you want to analogize it, all right? And it's just that you have more fish and less fish, and more fish and less fish. You wouldn't call that a wave, all right? Anyway, I mean, you can model it that way, but I'm just saying it's not what it's really doing. Alright, so I guess I'll have to erase this to be able to draw more, so that's what I'll do. And something like that anyway. Alright, one of the points I want to get to is this idea that the speed, okay, can be changed by putting things through it. They can change the speed of electricity, or you can change the speed of light by traveling through a medium. And this is what they use the jargon. Now, I can't say that he really believes that the speed changes, because I think he does understand that the matter's in the way, and all you're really doing is changing how fast the matter moves, not changing how fast the force moves between the pieces of matter. So it's just sort of a lie to say you're changing the speed of the, I mean, you can say the propagation of the force, but I mean, even that's just cheating the argument a little bit, because the force is a constant. It has one speed. It's always traveling the same speed, and all you can do is put obstacles in the way. And you really wouldn't say the force is going slower because you ricocheted it off of objects kind of argument. So it's this argument. Now, if I move my hand slowly, you can understand that I'll collect more light. More photons will be hitting my hand as I go from point A to point B. If I move quickly, less photons, less reflection. This is the difference between a high frequency and a low frequency. High frequencies are short movements, less bits, okay? But obviously they're more compressed. So you're compressing fewer objects more, all right? And those are the differences between frequencies. So in this argument he's making, he's going to try to, he uses water, which you could have just done a piece of metal or anything that's diamagnetic. So he puts the wire in water, simulate that in some way, water, water, it's water. Okay, so for whatever reason. That's what he chose to do. Okay, and so the idea is you're trying to inhibit the speed, okay, of the electricity, but you really can't do anything to the electricity. The electricity is the force between the electrons, right? So that, you're not going to change the fact that that's moving the same speed. All you can really do is inhibit the progress of the electrons. So the idea is that the electrons, okay, as you move them in the wire, they're going to cause an effect in the water that's going to create an opposite field, an opposing field. That is, it's going to be like more electrons on more electrons. So you're creating more electrons forward of your position, essentially, okay, to inhibit the movement of the electrons. And the trick is that if it's a high frequency, it doesn't have much effect, and if it's a low frequency, it has more of an effect. So if you want to cause more of the effect in the water to inhibit the flow of the electricity, the idea is to change to have the electricity moving electrons more distance, not shorter distances, lower frequencies than higher frequencies. because it's the density argument. It's more electrons. I mean, you know, it's a higher volume of bits of energy, okay, that you're going to be pushing in and pushing back with. And that's what you need to be able to, it's like you need the wattage, so to speak, to be able to suppress the movement of the electrons. It's okay-ish answer, but yeah, I'd like it to be better than that. But anyway, but you're not really changing. The point is you're never changing the speed of the force through the wire. You're just changing how much the electron contribution is in terms of changing the electrons from moving short distances to moving larger distances at a slower speed. So you're changing the rebound time, you could almost argue, of you know, how long it takes for the electron to go back to its previous condition, you know, to do its journey. All right. So there was something else I wanted to get to, so I'll pause to think of that. Yeah, I just wanted to make sure. See, one of my axioms is, one of the things you need to understand any of this, is that single electrons don't make photons. So I can't move a single electron from one position to another position and say, there, you know, I've moved force. The force has a frequency, okay, that I've increased by moving into it, and that somehow, I mean, you can understand, see, if a light was coming at me, I can blue shift it by moving my hand this way, and I can red shift it by moving my hand this way. Okay, so the reflections will mimic that fact. So that's a good axiom. We could say we agree on that. And that's all the electrons are doing. But that in itself, this tiny bit of stuff, okay, this little ray that's coming off an electron, right? The electron could be moving this way, or it could move this way, it could move this way. Whatever way it's moving, it's a tiny little thing, right? So when it moves into the field, it hits the oncoming force, reflects it, okay? And that's the key ingredient. It reflects it back. And that reflection is what the original energy, the original force going into the electron isn't what you're really seeing. What you're seeing is a reflection of another piece of force back to the universe. So in a sense, it's not the same piece of force that's traveling. It's just traveling in the sense that you've crashed two things into each other. All right, and you could argue that if these two things crash, this one reverses direction and this one reverses direction, or you could argue that one goes right through the other, or you could argue that they miss each other and it's all the same outcome. You have something going this way and you have something going that way. That's the important part. So when something's going this way, a force bit, and there's a piece of matter in the way, it's going to end up producing probably a piece of force going the other way. Anyway, if this piece moves. All right, the piece of matter. So I guess that's what I'm really trying to say here. This is just about the little bits of force going the speed of light, and everything else is matter, electrons and protons, and that's all you're moving. And that's another little part, a little subtle part of his video, was he was getting this whole, you know, he starts talking about the places where the electrons are orbiting, you know, they're, whatever they call them, they're foggy bubbles. And, you know, how you're moving those, but you're not changing the nucleus. And so it takes time to change the nucleus. Well, the nucleus has electrons in it, so that's, you know, part of the neutrons. The neutrons are electrons and protons, so there's electrons in the nucleus. So the nucleus is getting pushed. It just doesn't push as well as these electrons do. And the other point to make is that the electrons are wobbling. So when you hit them, they, just like something on Earth, like a spring, yeah, they push into the force pushes them back, but as they're going back, they're going back for a reason. It was because it was a good place to be. They weren't in the location they were in because there was pressure pushing them out. They were in the location they were in because the pressure was equalized. So obviously when you push them out of that equalized position, there's going to be an inequality that's going to put them back where they were, or head them back in that direction, and that's when they overshoot, and then they just do the wobble thing until they wobble down. So they wobble, the energy is dissipated through drag, and you know, it wobbles down to nothing. but the frequency is all the same. So when it's almost dead in terms of its energy, it's still the same frequency. It's just fewer bits of force that it's pushing. The amplitude, the amount is changed. Okay, but that's all that's being created are these little bits at a frequency. And they on themselves, I mean, one little ray of that can't do anything. Okay, it's not going to be a photon. A photon is when you have a series of it, okay, hit a series of atoms or electrons. That's when you can create the electricity that, you know, one of them hits this atom, then that atom's electrons vibrate. That vibration is felt by this atom next to it. They start to vibrate. This hits at the right time to put more energy into the vibration. That is, it's pushing it. It was going, the electron was going this way. You hit it with more energy, pushing it even faster this way. And so once you get them up to speed, then you can eject an electron, or you can create electricity because you're basically pumping the electron through the atoms, and you're just duplicating exactly what the atoms are doing when electricity is traveling through atoms. You're just duplicating it, and you've duplicated it from the exterior. And so that's how we see photons, as we see the electricity they create. That's how our eye sees a photon, is it makes the photon into electricity. I mean, that would be one of the important things to say before all these videos. Like I said, there should be things that are important to say. So maybe I'll just say the important things and you know, reiterate that he should do a kinetic energy video. Gotta get him to do a kinetic energy video. Prove kinetic energy, 1/2 mv squared. Do an experiment where you show it actually happening. Show the lever making the free energy. Show it. Alright. Yeah, so in some sense there's no point in going through the axioms, just because, yeah, you're not going to accept one of the ones that's most important, and that's the polarization one. You know, the fact that there's a proton force and an electron force, and they behave inversely. So if you don't get that one, a lot of the dynamics are lost. But there really just is a huge difference. Force is a thing, okay? The force is particularizable. That is, it's quantizable. Alright, so you can understand that there's a tiniest bit of energy in the universe. And that's when a bit of the force hits an electron, and you watch the electron do a thing, which is move. And when it moves, it changes its position in a field of force. And as it changes its position in a field of force, let's understand that the electron is assumed to be at equilibrium. Okay, I mean, it doesn't produce anything. It's not a burning sun. It's not a thing that has its own motor. So it just does what the field does. Whatever the field, if there's an extra arrow here, okay, then it's going this way. But if it goes this way, it's going into more force, so then it's going to stop going that way eventually. And unless if there's nothing compelling it to move back, then it'll stay where you put it. But there's always, electrons are always compelled to go somewhere. But you can sort of understand, if it was a charged universe and you had this stuff called plus and minus, there would always, no matter where I go, I'm going to find there's a little bit more plus and a little less minus. There's no, you know, finding a perfect zero in the universe would be highly unlikely. Anyway. So electrons are always wanting to be somewhere else, unless you can create a strong enough field to try to keep them in a position. But even when they're in that position, they're still going to be wobbling about, because there is changes happening around them all the time. The sun supernovas, some other event happens somewhere, and there's a little bit of extra crap hitting it. But anyway, so I want to get back in. It's not the argument I'm making. All right, so you got force. That's doing all the movement. So everything that moves only moves because force is pushing it. So an electron can't go from one place to another unless there's a hunk of force that's actually pushed at that location. Then another piece of force has to hit it to free that piece of force. Okay. I don't know if you have to have that axiom, but you have to sort of understand that's how the motion works. That the only way the force works is to understand that it's going the speed of light. If you want to make gravity, for example, then when it hits an electron, it has to actually stick to the electron and now move less than, okay, the speed of light. And now you've essentially consumed a little bit of the energy of the force. The force would have been here, but because it's pushing matter, it only got to here. That little piece of energy is what the Earth is excreting. Is this lack of energy is what's missing coming out of the Earth, right? All the atoms in the Earth are moving. All the electrons, all the protons, all the neutrons, all the little bits are moving. Every time they move somewhere, it means a force had to stick to them and push them there. And so every time that happens, this little hunk of energy is lost. And so the Earth excretes less than goes in. So it's not at a perfect equilibrium. That's the gravity that sticks everything to the Earth. See, I mean, I think you do have to kind of have a mechanical... You have to have a particle theory of gravity if you're going to understand a particle theory of anything else, frankly. I mean, it just makes sense. It's all moving the same speed. All the forces are moving the same speed. And so all you're really doing to the forces is just changing their appearance a little bit. So photons, it's about having a frequency. Charge, it's about being X and Y. You know, X and Y. You know, I would just say you can just do it with colors. Okay, understand that the proton is red and the electron is green. All right, and there's a green force and there's a red force, and the two forces are inversely related in the sense that if a red force goes into a green object, it comes out green. If a green force goes into a red object, it comes out, whoops, I shouldn't have done that. It comes out green. Okay, so should have been a green line. Yeah, the green's almost out, I guess. Too bad. I need it. Let's see how much I got left. Oh, yeah, it's about dead. Alright, anyway, not important. And then otherwise, if a green hits a green, it pushes it, sticks to it, and pushes it. So that's all you need, a simple little tiny rule. You just do that, and you can understand how protons are always excreting red, and electrons are always excreting green, because any red force is converted into green force. And all the green forces stick or get reflected. So if one sticks to it like an electron, it's got a piece of force stuck on it, and it hits another green force coming this way, they both reflect. You could sort of understand that's going to happen. It's an equal and opposite reaction. And then this stops moving, goes back to not moving again. And that's all the electron is doing. It's just looking for those imbalances, and it's just moving based on the imbalances in the field. Okay, if you have to use the word field, in the field of force. Field of force. Okay, come on. It's not that bad. It's not that tough. But anyway, you know, they're going to just turn it all into some magical wave thingy or field of waves and whatever. Some sort of thing is oscillating as it's going through space. It's doing this kind of stuff, and you know, it's just a pile of crap. The force is all moving in dead straight little lines. It's all little bullets, and the only way you change the direction of the bullets is to have them hit something. Okay, and then you can change their direction. But otherwise, they have to hit matter. They can't hit each other. Alright. That's probably enough of a video. I don't think there was anything else he said in the video that's that important. But again, it would be great if we can get him to do a nice kinetic energy experiment. Prove to me it takes 4 times more gas to go twice as fast. Show me. Yeah. You know, show me the 8-pound bowling ball knocking down twice as many pins. You know, show me. Or somewhere where your theory that, you know, light, fast things have more energy than slow, heavy things. Show me. Yeah, enough of a video. Alright, so till the next time. Put this one on the YouTubes. Ew. Yuck. Oh, yeah, I did want to add a little bit. Somebody left a comment, and you know, it's exactly what I'm kind of talking about. Okay, he has his own theory. There's not going to be any interaction regarding this theory. He's just going to tell me what he says a photon is, And there's not going to be any interaction or exchange or useful dissection of whether or not what he says is the truth, or she. So it says a photon is an image or waveform. I mean, these aren't useful words, frankly. Okay, it's not an image. I mean, come on, it's not a photograph. What do you mean, a hologram? What are you talking about? Anyway, of the particle in question. What particle in question? I mean, what, I can understand particle is electron. That's a material particle. Proton, a material particle. Now you tell me what the other material particles are besides what might be called a force bit. But there's nothing to cast images on. Okay, anyway. In a static universe, so again, this, I think he means a universe where you have a on and off switch. So at any moment you can take a picture of it. And everything changes a Planck distance. So in the tiniest amount of distance something can move. So everything just jerks into a new position. So it's a jerk universe. All right. In a static universe, each state can be modeled as an interval of collapse and reformation. So he's basically just saying that it's a stuttering universe. So there's no gradual increase. It either is here or it is here. So it's like a checkerboard. It can only be in the square. It can't be in between squares. Okay. Of the particle object. Successive states from a virtual diagram of overlapping rings are photons. So again, this idea that a photon is a ring, or that it's not a dead straight line thing. Okay, photons travel insane distances in dead straight lines. It's not going everywhere. There's not a photon and it decides whatever thing I hit first, I'm going to be a photon. That's just nonsense. Sorry, it's just nonsense. Photons are things going in a direction. Anyway, I mean, it's sort of provable. I mean, there's the photons on the opposite side of the sun are not ringing all the way over on this side of the sun. You know what I mean? The photons can't go both ways. It's not some sort of ring. All right. Anyway, image, the parallel processing of which is the straightforward expansion of time-space. So he's got an image of this. This ought to be really frightening. Yeah, okay, sure. The above illustration, a spiral cross-section of space-time diagram. So again, this is sort of like useless. Why would I care about this fake fourth dimension you've turned time into? You can't change time. It's the same time everywhere in the universe. It's just bullshit. It takes time for things to go across great distances. Whatever, blah, blah, blah. I'll read this on my own time. Thank you very much. Sometime later. Oh, I have to go back from here. No, where? Oh, comments over here. Sorry. All right. Comparison gives compression. No. Whatever. It gives the quantum wave function an object a new home inside the collapsing object themselves. So this all sounds way too complicated. Okay. So forget it. Yeah, you're not convincing me. Without the wave function, whatever the hell that is not only has no home, but fails to coincide with the logically evolving system of whatever this is, predicates of law of physics. CTMU. I don't know what that means. So why don't you make videos? I mean, you don't have any videos on your channel about any of this crap. So you really think you're going to convince me with these 2 paragraphs and a crappy drawing? You really think so? That this is, I'm going to say, oh yeah, this is what is happening in 3-dimensional space, is this horse shit, whatever this horse shit is. I don't think so. So anyway. But this is the communication breakdown. Okay, instead of staying on my subject and explaining how I'm wrong, he wants me to figure out what he's talking about and then prove him wrong. Okay, I guess. But that's all that can happen here. This doesn't have any consistency with anything I'm talking about. I mean, it's completely inconsistent. He does have red and black and blue, so at least he's using the right colors. But I'm sure they don't have anything to do with anything I'm talking about. All right. So, but yes, you know, you can't. It's got to be, like I said, we've got to find somebody who's capable of making arguments about why anyone should believe something. I mean, if you're going to tell me a force is some sort of ether or it's some sort of field of well, then to tell me what it is. Draw me a picture of it and how it functions. But this isn't going to fit into my three-dimensional universe. So if you can't make the picture of it three-dimensional, if you can't illustrate it in some way where I can understand it, you know, it has to be a pie or a rabbit or a tree. It has to be some kind of thing. You can't make it out of square. Square is not a thing. You can't just put a square in space and say, there, space has a square in it. What? And the square does something. Well, what's this way? How does the square do that? I mean, I'm going to ask the obvious questions. It's like Bill Gates and his stupid rope theory. I mean, just believe it. Believe that every single electron is connected to every single other electron with a fucking rope. I can't. What do you mean? It's impossible. All the ropes get tangled. You can't have, ropes have to be so tiny. How could I, it's like insane, these small ropes. Yeah, anyway, just too silly. Anyway, till the next time and such and so forth and whatnot. I'm kind of on a down ebb because it just seems like, well, it's really futile having any kind of conversation with human beings. They just don't want to deal with anything in any kind of rational, logical way. They just want to believe crap. Unfortunately. Alright, till the next time and such. This has been DraftPhysics.com. You heard it here first, and it really is the last word. I mean, I am going to be... Well, it just depends on how long the human race lasts. So if thinking has any future at all, I am going to be right. Okay, you're going to learn the truth eventually. You might as well learn it now.